In this video, we are going to draw different ways of drawing, and we are going to learn different ways to draw enantiomers. One is by perspective formula, and the other is by Fisher projections. Okay, perspective formula and Fisher projections. Now, we already talked about perspective formula before. For example, if I draw this molecule with a chiral carbon atom in this manner, with a CH2, CH3 here, and a CH3 here, I have a chiral carbon atom with a CH2, CH3 coming out with a wedged bond, and then a CH3 going at the back with a dashed bond. Okay, so this will be an example of a perspective formula. Now, if I were to draw the enantiomer of this, I only need to swap two of the groups, right? So if I draw the molecule by swapping what was at the back to what was in the front, I will get the enantiomer of this. Okay, so now we have CH2, CH3 here. Okay, so this represents a pair of enantiomers, and you can prove that by figuring out the R and S configurations at the chiral center. Let's do that. So in this case, we have let's take a different pen here. Okay, so let's give the priorities. We have bromine number 1, we have CH2, CH3 number 2, CH3 number 3, and hydrogen as number 4. Okay, now since hydrogen is not at the back, we will swap it with the group that is at the back. So you can have 4 here and 3 here. Okay, now your lowest priority is at the back. Then you do the rotation clockwise or anti-clockwise, but in this case you go from 1 to 2 to 3, right? 1 to 2 to 3, which is a clockwise direction. 1 to 2 to 3 looks R, right? Looks R, but is actually S, right? Remember, we talked about if you swap, you have to swap your answer too. So since we did the swapping, one swapping, so you get your answer as S. Okay, so the configuration at this carbon atom is S. Okay, all right, now let's look at this one. Let's do the priorities like before. We have 1 bromine, 2 for CH2, CH3, 3 for CH3, and 4 here for hydrogen. Now we are again going to do the swap where the lowest priority is swapped with the group that is at the back. So we have 4 here and 2 here. Okay, so now when I do the rotation, I have 1 to 2 to 3. Okay, 1 to 2 to 3. So I'm going this way, which is anti-clockwise. So it looks S. However, we have swapped the groups, so you have to swap the answer. So it's actually R. Okay, so the configuration at the chiral center is R. So one is S, other is R, which proves that we have a pair of enantiomers. Okay, now there is another way of drawing molecules, and that is called as Fisher projection. It's a shortcut for a three-dimensional arrangement. We can draw a molecule in a Fisher projection with an asymmetric center. So for example, a Fisher projection is represented in this manner, where if I put a CH3 here, I put a hydrogen here, a Br here, and a CH2, CH3 here. So this carbon atom has 4 different groups, so that is my chiral center. Okay, the carbon here is my chiral center. So how do I assign R and S configurations in a Fisher projection? So let's look at the steps. The steps are, first you assign the priorities like we did for the perspective formula. Okay, so rank the groups that are bonded to the asymmetric carbon atom or asymmetric center. Okay, so let's put that here. We have bromine again as 1, this as 2, this as 3, and this as 4. Okay, now in a Fisher projection, the horizontal bonds are the ones that are coming out to you. Okay, so let me redraw this molecule in such a way that it's clear that my horizontal bonds here are actually coming out of the plane. Okay, so this is my horizontal bond, and then the vertical bonds are the ones that go behind the plane. Okay, so we have a CH3 here and a CH2, CH3 here. Okay, so basically in this molecule, our fourth group, which is my hydrogen, is lowest priority, is actually coming out to you, right? But we want it back in order to assign the correct stereochemistry. So when I do my wheel rotation here again, I have 1 to 2 to 3, right? I'm going from 1 to 2 to 3. So it looks like it is S, but since my lowest priority is in the horizontal bond, this molecule is actually R at the stereocenter. Okay, its configuration is R. Okay, let's do one more example, right, on Fisher projections. Okay, so we have again one chiral center in this molecule, and I'm going to put a CH3 here, a hydrogen here, an OH group here, and a carboxylic acid group here, C double bond OH. Okay, so again our first step is to assign priority. Number 1 would be OH. Number 1 would be OH. Number 2 would be my carboxylic acid group. Number 3 is the CH3, and this is my fourth group. Okay. Now again, remember that the horizontal bond represents groups that are coming out of the plane, or you can think that horizontal means hugging. It's coming out to hug you. So they are coming out of the plane. So when we look at the wheel, we are going from 1 to 2 to 3, right? We are going this way. Our wheel is clockwise here, 1 to 2 to 3 clockwise. However, we know that if the lowest priority is on the horizontal bond, we need to switch our answer. So it's not R, but it is actually S. So the stereochemistry at the chiral center is actually S. Okay, so it looks R, but since hydrogen is on our horizontal bond, which is our lowest priority, we need to switch the answer. Okay, so if you were asked to draw the enantiomer of this molecule, the only thing you need to do is swap the two groups. Okay, so you can draw the enantiomer of this by again putting carboxylic acid at the same place. OH also can stay in the same place. You just need to switch it, the two groups, which is CH3 and H, right? And you can check if you have it correctly drawn the enantiomer or not by again putting the priorities here, 1, 2, 3, and 4, right? So remember, when we go from when we do the wheel, you always have to go from 1 to 2 to 3. So here we are going from 1 to 2 to 3. Looks like S, but actually it will be R, because again, since hydrogen is not on the vertical bond but is on the horizontal bond, so the configuration is actually R. So here we have the configuration as R. So since one is S and the other is R, we have a pair of enantiomers. Okay, let's do one exercise here. Okay, the question is, do the following structures, let's write down the question, do the following structures represent identical molecules or enantiomers. So if they are enantiomers, remember, they will have opposite stereochemistry. Okay, one will be R and the other will be S. If they are identical, they will both have the same stereochemistry. They will either be both R or they will both be S. Okay, so I'm going to give you an example here. We have a carbon with a CH3. These are simple examples so that you can understand the concept. And then we can put a CH2, CH3, and then a hydrogen here. And then the other pair is COH. I have a CH2, CH3, CH2, CH2, CH3. Then I have a hydrogen that's sticking out, and then I have a CH3 here. Okay. Now you have to look at these two pairs and tell whether they are enantiomers or identical molecules. So the best way to figure that out is to assign stereochemistry at the chiral centers, and we know that these two carbons are the ones that represent the chiral centers. So let's put the priorities again of the groups. This is 1, this is 2, and this is 3, and this is 4. Now in this case, the lowest priority is already in the back, so you just go from 1 to 2 to 3. There is no need of switching anything. We just go from 1 to 2 to 3. It goes this way, right? The clock goes this way, which is S. This represents the S configuration. Okay. 1 to 2 to 3. So it is a S configuration. Now let's try the other one. Here we have priorities 1, we have 2, and we have 3, we have 4, right? But here we have to do the swapping because our lowest priority is not at the back, so we swap it here. We go from 1 to 2 to 3, right? 1 to 2 to 3. It looks like it is, we are going from 1 to 2 to 3, right? So it looks like we are going anti-clockwise this way. So it is S, looks S, but is actually R. So what do you think it is? It's an enantiomer or identical molecules. So this actually represents enantiomers. Okay. All right, let's do one more here. Let's do a Fisher projection. Okay. Just thinking about, oh, sorry, let me take a black pen here. Okay, let's do this one. This is a Fisher projection now. Now we have a CH3, we have Cl, H, and CH2, CH3. Okay, so again remember, horizontal bonds are coming out to you, vertical bonds go at the back. And I give you the other pair which looks like this. We have a H here, we have a Cl, CH3, and then we have CH2, CH3. Okay, so let's assign priorities first. Here number 1 is chlorine, number 2 is CH2, CH3, and number 3 is CH3, and number 4 is hydrogen. Now remember, hydrogen is already at the back because our vertical bond represents a bond going at the back, right? So since hydrogen is already at the back, we can just do 1 to 2 to 3. We are going clockwise, so this represents a R configuration. This represents a R configuration. Now in this case, let's do the priorities again. We have chlorine still as number 1, this as number 2, this as number 3, and hydrogen as number 4. Now we are going from 1 to 2 to 3. However, remember, hydrogen is in the horizontal bond, right? So if we are it looks like we are going 1 to 2 to 3 R, right? R, but it's actually the S configuration, okay? Because hydrogen is at the it's in the horizontal bond, which means it's coming out. So whenever the lowest priority in a Fisher projection is on a horizontal bond, remember to do the switch for your direction of the clock which you are moving. Okay, so we have 1 to 2 to 3, which is an R configuration, looks R, but since hydrogen is on the horizontal bond, we have to switch our answer, and this represents a S configuration. So again, we have an example of enantiomers. Okay, now let's do one more, and then we'll end this video here. Okay, all right. So I have a group here, or a chiral center here with an aldehyde group. This is an aldehyde group, if you recall from your functional groups, and we have CH2, 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 OH. Okay, it's an OH here. Then we have a CH2, CH3, CH2, CH3, and then we have a OH here, right? And then the other pair for this is carbon. I leave the CH2 group intact here. Now I move some groups here. We have a CH2, CH3 now on the plane of the paper. We have OH coming out, and we have CH2, CH2, OH at the back. Okay, so let me change a little bit here. I think I put one extra, which CH2, which I don't want to put 3 there. CH2, CH2, OH. Okay, all right. So now we have two molecules which are isomers because they have exactly the same molecular formula, but we have to figure out whether they are identical or enantiomers. So we'll go back and try out our priorities here. OH is still number 1. This is number 2. Here this becomes number 3, and this becomes my number 4. So I'm going from, before we move, we have to do the swap because the lowest priority is not at the back. So I'm going to put 1 here and 4 here. And now I go from 1 to 2 to 3, right? I'm going this way, 1 to 2 to 3. So it looks S because see, it's an anti-clockwise, right? Looks S, but is R. Okay, so that is this carbon atom has a R configuration. Now let's look at the next the pair we have here. Number 1 is OH, number 2 is my aldehyde, the third group is this one, and this is my fourth, right? CH2, CH3. Now again I have to do the swap because CH2 CH3 is the lowest priority and it has to be at the back here. So after doing the swap, what do I get? 1 to 2 to 3, 1 to 2 to 3, right? I'm going this way. So it looks S, but is R. So here I have a case where both the chiral centers have R configuration. So that means this represents identical molecules. So I hope this video helped you to understand how to designate the R and S configurations at chiral centers, which include both the perspective formulas and the Fisher projections. Okay. All right. We'll talk about how to change a line bond formula into a Fisher projection and how to change a Fisher projection into a line bond formula in our next video.